We are starting chapter 10 tonight. Chapter 10 is very, very exciting. It's one of my favorite parts of everything that I get to teach in 143. I will admit that I probably have a little more fun than the typical student does because there's some of this that gets a little deep, a little hairy. There are some formulas. In a typical semester, there is a lot of memorization, or at least a lot of new things. There's not so much memorization because despite having a lot of formulas, we actually give you a formula sheet for chapter 10. We don't for any other of the chapters, but the department does allow us to have a formula sheet for chapter 10. I will myself I'll post the formula sheet that they allow you to use, and then I've made up this own formula sheet of my own, and I will probably show that to you, not tonight, but maybe Tuesday and maybe next Thursday. We expect chapter 10 to take about 3 sessions, so we will only get our feet wet tonight. We won't be up really past our knees because there's some mathematical derivations that we will want to do, and I'll go ahead and do them. So here's Greek mathematics, and here is algebra. And what we said about Greek mathematics, I'm indenting a little bit to have a subtopic, is that Greek mathematics was geometry. It was the study of shapes. And algebra is, well, it's algebra, right? It's manipulating symbols. And so we have all these symbols and we have rules for what we can do with the symbols. And what happened, so this is one of my favorite parts, is we get to connect everything. And who comes along, and you all know who it is. It's Rene Descartes. Rene Descartes, smartest man alive. And he combines the two topics into one field, which he calls analytic geometry. And what that allows us to do, Rene Descartes' analytic geometry has these XY coordinates, right? And so there's your x-axis and here's your y-axis. And the Greeks recognized a certain sort of shape that looks like this. And you're all thinking, oh yeah, parabola, that's a quadratic. And what Rene Descartes would say is he would say y equals x squared. And we've learned since then, this was not something that existed at the time of Rene Descartes, but we've learned there's an even more powerful way to express this as a function. And so we will often say the quadratic function f of x equals x squared. But for most of this chapter, chapter 10, we'll just think of y's and we'll think of x's. So here's the thing that we will start with. We will start actually on each of the sections. We will have these different shapes, and on each section we will start on the Greek side, and we will talk about how the Greeks saw these shapes, and then we will move over to the algebra side and we'll derive a formula from the Greek definition thanks to Rene Descartes. And from that definition, we'll have a formula and we'll have all kinds of analytical power where we'll have so much more understanding and control over the shapes that these Greeks passed on to us as their mathematical heritage. So, does this sound exciting? I don't know if it does. I'll show you how exciting it is. I actually have a shape. And if I hold it up so you can see it, and there's no trick to it. It's not like a magic trick. The shape has been cut in a certain way. Yes, obviously it's a cone. It has a circular bottom and it's pointy at the top, and this is a cone. And what the Greeks noticed was that if you cut the cone in certain ways, you would get different shapes. And these are very common shapes, and you'll recognize most of them. This particular cone, by the way, I want to thank the Makers Club. So this is an organization of CWI students, but if you have an interest in making stuff, so this is actually a 3D printer model, and I went and asked them, hey, could you make this for me? I want to use it for my classes, and they said, sure. So thank you to them. If we were in class, I always pass this around, and I tell you, be careful, don't drop it, but yeah, it's fine. So what's the idea? Here's this cone, and I don't know if you can see, but this line goes through the base. It's a cut, and we have cut, I think I can take my hand off it without it falling apart. We've cut straight up and down. So if you imagine the cone here, and I don't know if you can tell. Can you tell that the line pretty much goes straight up and down through this base? And it makes a shape, and you think, oh, it's a parabola. Doesn't it kind of look like a parabola? And it kind of does, but it's not. This is the one shape you probably won't recognize, but that's all right. You'll learn about it in section 10.3 when we get to these. I'll spoiler alert, it's a hyperbola. So it's not a parabola, it's a hyperbola. I might tell you a story about the guy who invented all these names too. If you cut, so here again, let me hold this thing, through the base, but at an angle, right? It's not going straight up and down. Well, you can't see my thumb moving. It's not going straight up and down. You can see that this cut is more of an angle. Well, then you get a shape. And yes, this is a parabola. This is the parabola that we've studied as y equals x squared. And we'll see why here in a few minutes, why we can write it as y equals x squared. The Greeks had a different way of defining it, and that's kind of interesting. If you cut, can you see it? Not through the base at an angle. So we're not going through the base. We're not going through the circular bottom. We're going through the side of this thing, and it's at an angle. And if you look at this shape, if I can hold it properly, there you can see that it is an oval, right? And we're math people, so we're not going to say oval. We will say ellipse, but it's the same idea. Last but not least, there are only 4 of these cone cuts. You could call them cone cuts, right? We're cutting through a cone. The last one is we're going to slice through the, not through the base, and we're going to go straight across it. So we're parallel to the bottom. There's a circle on the bottom, and we're cutting parallel. And this one's kind of tight, but if I can get it off without dropping the whole thing. Anyway, it's and it has a stick on it that holds it together. The stick isn't actually part of it. What it is it's a circle. Well, maybe you can see. There's the circle, and you can see it's perfectly round. And so that's how that goes. And this guy is not perfectly round. He's elliptical. He's more oval shaped. He's ovoid. He's more egg shaped, if you want to say that. That's where the word oval comes from, right? Ovum is an egg. So anyway, this is a cone, and we have sliced up the cone. And I will tell you that the Latin word for cone is, well, it was cone. It was a lot like cone. And the Latin word for cut was sect. And so we have things like bisect. You can cut things in two. You can cut open an animal. That's a dissection. Anyway, a section is a cutting of something. These 4 shapes, the hyperbola, the parabola, the ellipse, and the circle, are called conic, because they come from a cone, conic sections. Let me share with you the textbook, and we'll go through some of this, and we'll get a little ways, and then I'm going to insist that I do the math, because I like doing the math. I like to draw my own picture. The reason I like to draw a picture, well, here's the thing. This is what I find with students, is if I say, there's a really cool picture at the page 721, you should look at it. Well, 2 students will look at it. And if I draw the picture on the board, well, almost everyone in the class will draw the picture in their notes, because they're writing down what I put on the board. And so that's why I like to do it. Plus, I like to do it just because it's kind of fun. This is analytic geometry topics. Oh yeah, that is what it is. That's what we're going to do in chapter 10. I told you why it's called analytic geometry. This is a word that comes from Rene Descartes. And so this is interesting stuff. The analytic means there's some algebra in it, and the geometry means, and it's about shapes. And the book, in order to motivate you, you know, they always have an interesting picture at the start of each chapter. And what they want you to notice here is, if you look at this shape, this is a satellite dish, and you think, hey, it kind of looks like a parabola. And if you're thinking that, you are exactly right. If you cut a cross section, see there's section, you cut a cross section, then you do get a parabolic arc, a parabolic shape. So here comes a drawing that's a lot like my cone. The only difference is the book has two cones. Aren't they fancy? I only have one. That's all right. I only need one to show you what I wanted to show you. So here is the parabola. Notice that it's cut through the base of the cone and it's cut at an angle. Here's the circle. It does not go through the base and it's perfectly straight across. It's parallel with the base. Here is an ellipse. It does not go through the base and it is not parallel to the base. It's at some kind of a wacky angle. And here's the hyperbola, and it cuts not only through the base, I showed you that on my cone, but if you have these two cones that are nose to nose, tip to tip, point to point, then if you cut straight up and down, you will go through both cones, right? A parabola is angled in such a way that you only go through one cone. If you're going through both cones, then you're not getting a parabola. And it turns out, they tell you this, and we'll look at it and go, what? And then we'll ignore it for quite some time. We'll come back to this at the very, very end of 10.4, and we'll go, oh, well, that might be interesting. And in fact, the book does do more when they get to 10.5 and 10.6 and those other sections with this, but we won't do much with it more right now other than to just say it turns out that these four shapes, all four of them, can be described with one single formula. You think, well, how can a parabola, they're totally different formulas. Well, it depends on what these coefficients are, A, B, C, D, E, F. If you knew what A, B, C, D, E, and F were in this, and if you had a little bit of practice, you could look at this formula and say, oh, it's an ellipse. Or you could look at the formula and say, hyperbola. And you think, wow, how could someone do that? And the answer is, it's actually pretty easy, and you will do it on the next test. So yeah, that's kind of cool. It gives you power over the thing. So here's the idea of a parabola. We know this is our modern stuff. F of x equals ax squared plus bx plus c. Oh, it's a quadratic, and there's this thing, there's an axis of symmetry, and we learned how to find vertex, right? That's the gorilla thing. It's negative b over 2a, and okay. Anyway, it defines a parabola. It turns out we wouldn't have to do it with algebra, which is how we did it before. You can define it geometrically. This is how the ancient Greeks did it. So this is 200 or 300 years BCE. And the way they did it is they said, imagine that you have a point. Here's a point, and it's called the focus. And we'll find out why later. And imagine you have this line that's called the directrix. And you think, well, that's a stupid name for a line. Yes, you might think that. Remember, this is ancient Greece. Well, actually, these are Roman words. Yeah, they switch. The Romans and Greeks, they were like, well, you can't see. I'm holding fingers very, very close and saying they were like this. They copied ideas from each other. They exchanged ideas. Roman poetry is really Greek poetry. It happens to be in Latin. But the Romans didn't do a lot of innovative, hey, let's totally change the idea of poetry the way, say, the French did or the Italians did, right? Centuries later. Anyway, the Greeks and the Romans are doing all this math, and this word directrix, I want to talk about it because there's a way to remember what it means and what's going on. In English, we have people who are actors, and then we have people who are actresses. And the difference between an actor and an actress is that actors are traditionally men and actresses are traditionally women. And this is less true now because this is considered kind of sexist to make this distinction. And so there are many very, very talented female actors, and they call them actors even though actually they're female. 50 years ago, 60 years ago, if you said that, I don't know, think of an actress. My mind's drawing a blank. Sandra Bullock. If you said, oh, Sandra Bullock is an excellent actor, 50 or 60, 70, 100 years ago, people would look at you and say, what? She's not an actor, she's an actress. And you would think, well, that distinction doesn't really need to be made. Well, there are some languages where that distinction does need to be made. For example, if you are a Spanish speaker, studied Spanish in school, you know that when you talk about a white house, you say casa blanca. Blanca means house. And if you're talking about a white dog, you say perro blanco. And so blanca, blanco. And you say, wait, why do you have different endings for different, just because it's a what? It doesn't make grammatical sense in English because we say white, white. We don't say white house and white old dog, but they do in some languages, and they did in Latin. And it was very, very important not to call an actress an actor. And in particular, the word for a line, and this is a line, happened to be feminine. The way in English we say a ship is a she. In Spanish, a house is a she, casa. In Latin, a line is a she, and so directrix has to have the ending. This is a lot like actress. There was a director, which is an actor, and there was a directrix, which is an actress, right? This is the idea. That's not what they mean, but the endings are the same sort of thing. So this is, think of this as the directing line, and because lines are all female in Latin grammar, we call it a directrix. And so there's the mystery of that. So what are we doing? We've got a focus, we've got a line, the directing line, the directrix. So you have a focus and a directrix. And what you say to yourself is, suppose that I wanted to be some distance away from the directrix. So I'm going to be, and I don't know what your scale is on your screen. It'll be different from mine, but I'm going to say, suppose from here, the directrix to this point, and I can't mark the point. If I had the whiteboard, I could, but I'm trying to avoid doing too much of this drawing on the whiteboard just because it'll be hard. I'll draw it in a second. But here's the directrix and here's a point. And you say, well, how far is it from this point to this line? And if you have a ruler, you pull it out. And you don't even need a ruler, right? You can say, well, this is xy. It's some point, xy. And this right below on the line, well, it's x, and then the y is 0. And so this is x0, and this is xy. And how far is this point away? You'd say, I'm thinking it's y. And you'd be exactly right. How high up is this point? Well, what the Greeks did that was interesting is they said, now take this point, and how far is it to the focus? And I don't really know. It's hard to tell. It turns out the definition of the parabola to the ancient Greeks was, it's all the points, so here's a point, that have the same distance to the directrix as to the focus. And so if this is y inches or y feet or y miles, y millimeters, whatever it is, then from here to here is also y inches, y feet, y miles, y millimeters, exactly the same distance. And you think, well, how about this point right here? Well, it's not as far from the directrix and it's not as far from the focus. And well, how about way up here? Well, it's quite a ways from the directrix and it's also quite away from the focus. And the same thing on this side. And so they say a parabola is the set of all the points in a plane equidistant. That means they have the same distance from a certain fixed line, which is called the directrix, and a certain fixed point, and the fixed point better not be on this line or it doesn't work at all, and that point is called the focus. Right through the middle of the parameter there is a line. It's an imaginary line called the axis of symmetry, and yeah, axis of symmetry, that was like chapter 3 stuff. And yep, you're right. And the vertex is the midpoint of the segment. Notice that it is on the parabola. That means the distance from the vertex to the focus and the distance to the directrix are the same distance. That means if you have a little line between the focus and the directrix, the vertex is exactly halfway between the focus and the directrix. So here's an example of a point. Here's some point, and I told you it's called xy. And what's the point that the directrix is on? I don't know where the directrix is. Here's what we decided to do to simplify the notation for us, is we said that the vertex is at the origin. And having the vertex at the origin simplifies things. And you think, well, what if I want to put the vertex up here? What if I want it way off? And you shift everything, and you think, oh, shifting? That's like chapter 4. Oh, yeah, chapter 4. We learned to shift. And all those transformations apply. And so we'll be very, very happy when we get there, and it will all make sense to us. But to simplify everything right now, let's put the vertex at the origin. And we know that the vertex is exactly halfway between the focus and the directrix. And so if the vertex is at the origin, wherever the focus is, well, the axis of symmetry, since we're on the origin here, the axis of symmetry is the y-axis. And so this point, wherever the focus is 0 in the x direction. We haven't moved off the y-axis. And it's up some distance, let's call it p. So little p is this point that's the distance from the vertex to the focus. Well, we know that the distance from any point to the focus is the same as the distance from that point to the directrix. And so if the focus is at p, 0p, well, then the directrix has to be the opposite direction, right? It has to be at negative p. And so we have this line, because the directrix is a line, the directing line, and its formula is y equals negative p. And we think, oh, well, okay, this is so far so good. There's a point, and we're calling it f, that's the focus, and it's located at 0p, and we have this directrix, okay, and all the points. So here's a point, look, right there, point. P, see, capital P, that means point. And what's the name of this point? I usually ask my class this. It's almost a trick question. I say, hey, here's the point. What's its name? And the kids kind of look and they stare at me, and I say, come on, you know the name of a point. And they stare at me and look and think, what? Every point, this is the answer to the trick question. Every point there is has the name x, y. Every point is an ordered pair. So here's some point, and I don't really know where it is. It might be right there, but it might be up here, and it might be over here, and it might be, I don't know where it is. I'm being very generic. But I know that point, wherever it lies on the plane, is called x, y. So this is a very, very generic name. Okay, then, what's the difference? What's the distance from this point to this point? In other words, what's the distance from the point on the parabola to the directrix? And you say, well, it's PG. So that's the name of this distance, right? Does it feel like 10th grade geometry? I'm sorry to bring back dramatic events. Most students don't like grade geometry, and they're glad they got out of it. We won't do a lot of geometry. Don't worry, there won't be any proofs. But whatever this distance is from P to G, that's the exact same as the distance from the point to the focus. And the point is P and the focus is F. And so we say PF is PG. Okay, we got it. And then we think, wait. Back in chapter something, it was a long time ago, we learned a distance formula. We had this Euclidean distance, and so this should look familiar. D equals the square root of, and we have 2 points, right? x2 minus 1 squared plus y2 minus y1 squared, and we take the square root of that whole thing. And that's in your notes somewhere. I even showed you a derivation, how to get it using the Pythagorean theorem, right, with 2 points. And we did that a lot. So let's look at our points. I'm going to go ahead and redraw this. We've got a lovely, lovely bunch of coconuts. No, that's an old British song. We've got a lovely parabola, and this parabola has a point P, and its actual name is XY. And then there's focus. I don't know if this is perfectly to scale. What is this point? Well, it's 0, because we're on the y-axis. We're at 0, P. So there's this focus point. And there's also a directrix. And so here's the directrix line, and it's supposed to be straight across, but I'm writing in my lap. Have some sympathy, kids. Anyway, it's y equals negative p. There you go. So you go up p and you go down p, and these are exactly the same distance, and obviously drawing kind of messed up. It's not to scale, but you get the idea. So how far is it from here to here? That's pf. pf. And how far is it from here to here? This is pg. And we know the name of this point, it's xy. We know the name of this point, it's 0p. We know the name of this point. Wait, we do? Yes, we do. How far are we in the x direction? And you say, well, we're right under here, and so we're x in the x direction. This is very, very generic. I don't know what the value of x is, and I kind of don't care. And how far are we in the y direction? Well, we've gone down negative p. And so there's my... So far, so good? So PF equals PG. Let's put that. PF equals PG. Both of these are distances. And the distance from P to F will be the square root, and I'm just going to do this thing. So x2, this is my x2, my second point. It's x minus and x1, that's this first point, x minus 0 squared plus y2, that's y, minus, I'm just using the formula, the first point, that's p squared equals, sorry, this is taking two lines, equals, and now do this. So my first point, x minus, just following the formula, minus 2. I just got this x point, so there's some little dots. There's my x right there. And then I'm going to subtract this other x. Oh, that's going to be easy to calculate later. Plus, and now here I am at the y right there. So there's my y minus, and the point down here on the directrix is negative p, negative p squared. You can see the 2 up there. And then I'm thinking to myself, well, there's a square root on one side and a square root on the other side, and I'm going to square both sides. And so if I square both sides, I get x minus 0 squared. I'm thinking x minus 0 squared, that's x squared, because the 0 doesn't do much. Plus y minus p squared, and you think, gosh, I wish I knew what that... Oh, wait, the dance. Should I turn on the video and do the dance? Square it, multiply and double. So hey, I squared it. Negative p, I'm squaring it. Sorry, I pointed and you can't see it, of course. And then y times negative p is negative py, and I'm going to double that. Square it, multiply and double. So minus 2py. And so there's that guy. And then that equals, there's my equals. I already squared both sides, so that's gone. X minus x, well, that's 0. And so now what do I have? I have y plus p. I'm going to write it out. I don't want to do two steps at once. So on the left, let's do this. I've got x squared plus y squared minus 2py plus p squared. On the right, this gets just a little worse before it gets better, but it will get very, very soon. And you'll go, oh, that was sweet. So square it, multiply, and double. The first thing is a y. I'm going to square it. The last thing is a p. I'm going to square it. And then y times p, well, that's py, and I'm going to double it. So plus 2py. Can you read my scrawl? I think so. I hope so. I'm going to change colors because I'm going to go wild. There's an x squared on the left. Yeah, fine. There's a y squared on the left. Yeah. There's also a y squared on the right. Haha, they're gone, right? They both canceled out. I told you this would get better. Let's switch to purple because I'm in a purple mood. There's a p squared on the left. There's a p squared on the right. And the y's are gone. The p's are gone. On the left, I have x squared. There's my x squared. I also have a negative. I'm going to add this. Plus 2py. because I want to get rid of him. Plus 2py. Whatever you do to the left, do to the right. Whatever you do to the right, do to the left. So while those guys are gone, I have x squared on the left, a lovely x squared, and on the right, a 4py. And if we rewrite this now so it's pretty, x squared equals 4py. Is that cool or what? And you're thinking, no? Yes, yes, no, it is cool. Let me show you why. Let me show you why. This is cool. I'm going to type it out. This is the formula for a parabola with its vertex at the origin and the focus at 0p and the directrix at y equals negative p. And so, well, that's what we started with. Y is negative p, and the focus is at 0p, and the vertex is at the origin, and this is the formula. And this would be the thing where I would say, memorize this. And of course, you don't have to memorize it, not only because it's COVID time, but also because the chapter 10 stuff is just, it's just tricky enough. I don't think it's hard. I think it's different. I think it will feel new to you. I mean, you're looking at the last 10 minutes of exposition, and you're thinking, I don't want to have that. No, you'll never have to do that. That was me having fun. Thanks for playing along, kids. I appreciate it. Here's this formula, x squared equals 4py, and this is the formula that if we said to memorize, well, that's what you would have to memorize. And what's so powerful about it? This describes every single parabola. And you say, no, it describes a parabola that has a focus at 0p and a directrix at y equals negative p with the vertex at the origin. Well, what if the vertex isn't at the origin? Well, we'll give me a minute. Don't rush me. What if the focus and the directrix aren't right here? Well, wherever the vertex is, suppose that your vertex right here, and suppose this is your parabola, and you're thinking, well, that's a weird parabola. It's kind of flat. Well, yeah, you can have them that are kind of flat. And the idea is that if this parabola were really that flat, then the focus wouldn't be very far away. And the directrix, see if I can draw it straighter this time, wouldn't be very far away. And of course, I've messed this up here. Let me fix it. So this focus is really, really close, and the directrix is really, really close. And that's what makes it so flat. If the focus were way up here, well, remember that the focus, how far is it from the vertex? The same distance as the vertex to the directrix. So if the focus were way up here, then the directrix would be way down here, and you would have a parabola that was a lot tighter. I don't know if you can see that little hand going, but it's a narrow, skinny thing because, yeah, the focus is way far away. So there's the idea. Okay, so going back to this formula, x squared equals 4py. Your next complaint, and this is a legitimate complaint, is to say, that's not what we learned. We learned the formula, and I'm going to put this here. Compare our formula. It's in the lower left corner. I'm putting it in black. Y equals x squared. This is what we learned, right? So this is chapter 3. This is chapter 3. And this is chapter 10. And my argument would be, these are the exact same formula. And you say, no, they're not, because this has a y all by itself, x squared. Okay, that side, I mean, you wrote it backwards, which is goofy, but it makes, okay, there's an x squared, and there's an x squared, and yeah, you wrote it on the right and you wrote it on the left, but we know equal sign, it doesn't care. But what's wrong with it, the reason they're different, is this has a y in chapter 3, and this has a 4 times p times y in chapter 10. They're exactly the same. And you're thinking, no, they're not exactly the same. They're different because this has a 4p. X squared equals 4py. This is where we're going. There's Desmos. So let me show you the chapter 3 version. This is the chapter 3 version of a parabola. And what is the chapter 3 version? It's y equals x squared. And you look at it and you think, yep, that's chapter 3. I remember it. That's a parabola. That was the formula, and that's what it looks like. Perfectly good. Here comes the chapter 10 version of a parabola, and my claim is it's exactly the same. I don't need that. I can just type it in, can't I? And what did we just say it was? We said that it was x squared equals 4 times p times y. And you look at it and say, well, it's not the same because I can't even see what, look, it won't draw it. They don't know what p is. Oh, they don't know what p is? Well, I'll tell you what p is. P is 1/4. You say, wait, where'd the thing go? It's there. It just happens to be exactly the same. And so it drew over itself. And then you think for a second, oh, wait, it's a trick. Because 4 times p, if p is 1/4, then 4 times 1/4, well, that's 1. And 1's invisible. There's a 1 there. And so y equals x squared and x squared equals 4py are the same if p is 1/4. What does that mean? If p is 1/4, p is where the focus is. And we know that the focus is at 0p. And we could label it if we wanted to. There it is. It doesn't look quite as pretty. We also know there's a directrix line, and the line is y equals negative p. And there it is. And to really emphasize this is a directrix, what I like to do with my stuff that's not really part of the graph is I like to turn them blue, and I like to dot them. So there you go. There's a dotted line, and that's the, and we could zoom in a little bit. Let's zoom in just a little bit. And you go, oh yeah, how far is it from here to here? 1/4. How far is it from here to here? 1/4. Yeah, but how far is it from here to here? Well, that point is at 0.5, so this distance is 0.5. And how far is it from that point down to the directrix? And you say, well, it's 1/4 plus 1/4. Oh yeah, that's 0.5. Huh. And how far is it from here to here? Well, this is 0.25, negative 0.25, and this is 1, so it's 1.25. And how far is it from here to here? And you could go ahead and use that distance formula if you wanted and say, well, this is the 0.111, 1 minus 0 squared plus 1. And you could do all that work and you'd find, oh, it's exactly the same as this. And you might, I would encourage this, find a couple points that are friendly enough, I don't know. One is certainly friendly. Is this one friendly? Kind of, no, kind of not. What if we I'm trying to find one that's, anyway, find a few points and round them, just, you know, so you don't kill yourself, and try it out. Plug in the distance formula and see, oh, is that really how far the distance is? And you will find that every single time, yes, that is the correct distance. Well, that's great if this is the only parabola we're ever going to draw, but it's not. I told you if the p was really, really big, and so let's go back here. I wrote p equals 1/4. Let's zoom out just a bit. Zoom back out just a little bit, and let's make p bigger. Let's make p be maybe 2. You think 2? Oh, well, hey, it's flatter. I think I told you if it was farther, it would be tighter, and I said that wrong. The farther away, the flatter it gets. The closer it is, the tighter it gets. And so here it is at 2, and it's flat. And if we were at 3, say, well, it's still flatter, and 4 is flatter still. And in fact, Desmos will let us, if I erase the p, it says, wait, you have to define p. Do you want me to add a slider? And you can see this add slider, and I say, actually, I would like to have a slider. And there's the slider. And now I can click on this and I can move wherever I want. Oh, this is cool. Look at me go. Oh, this is fine, but what if you want a parabola that's upside down? Well, that's okay. We got negative values. There. There's a focus. The focus is at 0, p. P has the value negative 1.6. The focus is at 0, p. Where's the directrix? It's always at y equals negative p. Oh, and there it is at 1.6. Y equals 1.6. Huh. So anyway, do play with this to get a feel for what's going on. If you get the value, let's get a really, really small. Look how, oops, look how close that is. It's hard to get too tight. It's hard to get too tight just because Desmos being what it is. You're thinking, couldn't you make it really, really skinny? Yeah, you could. This slider is going to assume probably he wants to go by tenths, and what I would need to do is put in a 0.5. Actually, you can drag these. There. Is that close enough for you? Tight enough for you? And we could zoom in some more. I can click on the point and drag it. Yeah, there you go. There's a pretty tight. And if we zoom back out to our normal scale, oh yeah, that's a tight, skinny little thing because the p-value is, the focus is so close to the vertex and the directrix is so close to the vertex. They're the same distance. So we did this stuff and we got x squared equals 4py. And there it is, standard equation, 0, 0, directrix, blah, blah, blah. The focus is here, the y-axis is, yep. We know all this stuff. If p is positive, the parabola opens up. That was what I showed you. And if you want an upside down parabola, make p negative. Well, here's the neat thing, is if you look at this graph, this has a point P, and it has a line, which is a directrix, and you're thinking, wait, something's wrong here. This isn't a function because it fails the vertical line test. Exactly. It's not a function. If you caught that, you're doing good. But notice there's no f here. There's no f of x equals, this is an equation. This is x squared equals 4py. That's an equation, and this is the graph of the points x, y that satisfy that equation. This down here, y squared equals 4px, this is an equation, and this is the graph that satisfies that equation. It's not the graph of a function, because obviously this isn't a function. You can't do a function like this because it would fail the vertical line test, but it's happy to satisfy this equation. And what's going on here, instead of having, let's see if I can see both of them at once. There I go. Instead of having the focus at 0p, I have the focus at p0. And instead of having the directrix at y equals negative p, I have the directrix at x equals negative p. And this is kind of neat because it means instead of having parabolas that go up and down if p is negative, you have parabolas that go to the right or to the left if p were negative, if the focus were to the left of the origin. So we have these different formulas. The hint you want to know is you can always spot that this is a parabola because there are two variables. We're going to get into 10.2 pretty soon, and there will be two variables, x and y. And what you want to notice is in parabolas, only one of the two variables, I can't make this one light up, only one of them has a square. So here the x has a square, but the y does not. Down here the y has a square, the x does not. And if you think, well, this looks like y equals x squared, that's an ordinary parabola. And this, I've switched the x and the y. Exactly, you've switched the x and the y. I'm going to go back, I'm going to put it to 1, 4, because I liked 1, I got to key it in, don't I? I got to key it in. Why? Because I want a really generic parabola. And I'm going to zoom in just a hair. Good enough for me. And then I'm going to put this guy. Y squared equals 4px. And I could put a different focus, and so my different focus, instead of being 0p, it's going to be p0. There's the focus. And instead of having the directrix y equals negative p, I'm going to have the directrix x equals negative p. And again, because I like to do this with things that aren't really part of the graph, I like to turn them into dotted lines. I do that with asymptotes. I do it with directrices, with directrixes. And if you look to yourself, you think, okay, so there's this, and then this. Wait, Gary, hold on a second. I know what you did. This is x squared equals 4py. This is y squared equals 4px. All you did was switch the x and the y. If you switch the x and the y, what do I have? This was in chapter 5, right? Section 1. If you switch the x and the y, that's exactly right. And you think, he said they look like fishes. Oh yeah, they kind of look like, or maybe a butterfly. I don't know. Butterfly, butterfly, fish, butterfly. We could, in fact, be even more convincing to ourselves by putting our mirror line, right? And so there's your mirror line that we sometimes put in. Let's make it blue and dotted. So that would be like the mirror of these two. And oh yeah, if something's reflected over the y equals x line, then you know that it's an inverse. Okay, well that's kind of cool. So we just saw these standard equations, and they're called standard equations because they're really, really generic. The vertex is 0, 0, and you go up and down, or the vertex is 0, 0, and you go horizontal left to right. They show you a few examples. So here is a very, very, very small value of p, or is it, right? If you look at this, you say, yeah, y equals negative. No, that's not what the formula was. Look at this. There's a y, and then there's something times the x squared. Go back a page and let's look at the formula again. Remember, there's two different formulas. One has a y and one has a y squared. This is the one with a y. There's a y and there's an x squared. Oh, wait, you're supposed to multiply the thing by the y. You're not supposed to multiply something by the x squared. You have to multiply by the y. And so if we go back to this, you say, hey, you're multiplying by the x squared. You want to multiply by the y. So we multiply by the reciprocal of this. We multiply by negative 12. Well, minus minus makes a plus. It's gone. And 12 times 1/12 is 1, and we don't write it. And over here, multiplying y times negative 12, well, it's negative 12y. And then you think, there's a y, and I know it's multiplied by 4p. Negative 12 equals 4p. And you could do that as a little algebra equation if you want. Some of you will do it in your head, but you think negative 12 equals times p. Well, then p must be what? Negative 3. And there it is, right? 4 times negative 3 is negative 12. So where is the focus? It's 3 units away. Where's the directrix? It's 3 units away. This is a y equals x squared. That feels normal. Y equals x squared, and so it's an up and down, but p is negative, so it's upside down, and there you go. You got the guy, he's upside down. There's your focus at negative 3. There's your directrix at negative 3, which is positive 3, and you could sketch it. You can go the other direction. Someone says, quick, 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 I need an equation of a parabola. Oh yeah, well, what do you need? Well, the vertex has to be at 0, 0, and the focus has to be at 5. And so I will grab some graph paper. Here's my graph paper. Don't look at this yet. That's the answer. There's my graph paper. And he told me the focus is at 5, 0. And so I put in my focus. He told me the vertex is at the origin. There's the origin. And I say, well, wait, if the vertex is this far from the focus, it has to be the same distance to the directrix. So if the focus is at 5, 0, then the directrix has to be the line x equals negative 5. And that makes me realize, oh, this isn't a y equals x squared. This is an x equals y squared. And the formula with that, here's the x and here's the y squared. And the 4p gets multiplied by the thing that doesn't have a square on it. And we know what P is. They told me. It's 5. Oh, well, then y squared equals 4 times 5. That's 20. There. Formula. Y squared equals 20x. Alrighty. Let's move stuff around because we can do more stuff. Then we've got this generic parabola equation. And what was it? It was x squared equals 4py. And what's this going on? P is the focus. And I shouldn't just say P, right? I should say 0p. 0p is the focus. And y equals negative p is the directrix. And the vertex is at the origin, and I will write it out, 0, 0. Cool. What are we going to do? We're going to shift the vertex to some other point. I need a generic point. What did we call it in chapter 4 when we shifted stuff? I'm going to shift it to HK. And here's the weird thing about math. The reason I pick HK is because H is the next letter I haven't used for anything, right? Because you think A, B, C, well, you haven't used those. Oh, yeah, I did in the quadratic formula, right? There's ax squared plus bx plus c. So I can't use a, b, c. And how about d? No. D is for a distance. And so I can't use that. Well, use e then. No, e is like e to the x, right? The log base e. E is, that's Euler's numbers. 2.7 something something. We can't use e. That would be, okay, we'll use f. No, f is what we call functions. Well, then use g. No, g is what we call functions if we don't call them f. Well, do you have any letters? How about H? And we say, yeah, okay, H. I'm good with H. And so here's my generic letter, H. And that's how, literally, that's how we get this stuff. And we have normally, have I written it somewhere? I haven't. Normally we X, Y. Well, now we have, and that's X, and then the very next letter is Y. And so here's H, and then the very next letter is K. Oh, wait. The very next letter after H is I. No, we can't use I. I is the square root of -1. Okay, well, use J then. Don't be such a ninny about it. Use J. No, J is what physicists use for the square root of -1 because reasons. And okay, how about K? Yeah, I'm good with K. And so this is the idea. HK is some XY point, and it's generic. We're not claiming anything special about it. So if we shift the vertex to HK, well, we added H to the 0. We added K to the 0. What does that mean in terms of this formula? Well, what that means is, and you'll see how this goes, you'll think, oh yeah, this makes sense. This is an X, and it's squared. So X squared. Look up at the top in the blue and see X squared, and then look at the bottom and you say, yep, it's X squared. And then look up at the top, 4, and there's a P, and then here comes a Y. And this, I hope, feels a little natural to you from chapter 4. I have moved X and I have moved Y. How far? Well, they're centered at HK now. And so in a generic way, you have to shift back, right? This is the idea. This is X, and well, it's been shifted by H. So unshift it to understand what's going on. Here's the Y. It's been shifted by K. Well, unshift it. So this is now the, not generic, but this is the formula. What have we got? P. Up here, I wrote 0P. And down here, I can't write 0P. What I wrote at the top is I wrote P is the focus. P is the focus. And then I had to fix it because P isn't the focus. The point 0P is the focus. And I have to fix this one too. So here's my fixing. P is the focus. It's not really P, it's really 0P. Except it's not 0P because 0 has been shifted. 0 has been shifted by H. and P has been shifted by K. And so there's the focus. It's at H, P plus K, which is really it's really 0P, except I've shifted it by HK. Up here, y equals negative P is the directrix. And so what's the directrix? Well, it's y equals negative P. Well, wait. Didn't you shift it? Yes, I shifted it. How far did the y shift? The y shifted by K. And so it's negative P plus K, and that looks ugly, and so they typically do this. K minus P is the directrix. And that's the idea of it. Vertex is, I already wrote that. Vertex is HK. And that's what's going on. If you've learned x squared equals 4py, and that's okay because it looks a lot like y equals x squared, which we know is a parabola, and we just have this new way of thinking of it with this 4p. It's kind of a different kind of translation almost. The 4p tells us more about what? This focus and this directrix. That's what the p tells us. And here all we're doing is we're shifting it to HK. And so the shift changes the formula. Instead of x squared, we have x minus h squared. And instead of 4p y, we have 4p y minus k. And the focus gets shifted and the directrix gets shifted, both of them by a factor of k, because where do they move? They move in the y direction. The focus is up and the directrix is down lower, and so that's the y direction. If you had a sideways thing, if you had the other kind, y squared equals 4p x, if you had that, then again you would have these shifts. So this is the stuff I just showed you. X minus h squared equals 4p y minus k. So there's my HK, my new center, sorry, not center, X. And the focus is K above that, the directrix is K below that. And you think, well, if I'm at HK, then the focus, P above that, P below that is K plus P and K minus P. This all makes sense. This is the sideways one. And instead of y squared, they have y minus k. The trick is x, y, they're in alphabetical order. H, k, they're in alphabetical order. You move your vertex to HK. How does the x change? It changes the H. How does the y change? It changes the K. When you do this one, don't mix it up. X, Y, H, K. So what does the y change? It changes K. What does the x change? It changes H, right? And so it's kind of like, wait, these are all backwards. No, they're exactly the same. The H always goes with X. The K always goes with the Y. K always goes with Y. H always goes with X. And so how are we moving? We're moving a distance of P, and we started at H. We're moving a distance of P. We started at H. And how do you know that you move that distance? Because it's left, right. Well, then it has to be H, because H is the first letter, X is the first letter, left, right is X. Parabolas have a ton of applications. There are a crazy number of applications for parabolas. Cross-section of car headlights, flashlights, searchlights, satellite dishes, field microphones. Let me show you how it works. Usually I draw this on the board, and instead I'll just show you the picture. Notice that here is a shape of a parabola. Here is the shape of a parabola. Here's the shape of a parabola. And we know something about parabolas. Parabolas all have a focus point and a directrix line. And if you think that this bulb is at the focus, if you think that this receiver is at the focus, if you think that this no, this is a pot. This is a pot of rice, is at the focus. The remarkable thing about rays that, let's first talk about entering. Rays which enter the parabola in a parallel fashion. So where are these rays coming from? Well, these rays in this parabolic dish cooker are coming from the sun, and the sun's rays come down and they hit this shiny, shiny, shiny parabola and they bounce off. The rays here come from a satellite, which is orbiting the Earth, a geosynchronous satellite. So it's always in the same place and it's far enough away. Well, it's not that it's far enough away. The sun is far enough away that, yeah, it's parallel. The satellite is actually in a location, and when the person comes and installs the satellite dish, they have this fancy little reader that they plug in, and they actually aim this satellite dish at the satellite. So when the satellite emits signals, radio signals, they reach the dish in a parallel fashion. And what happens with a parabola, because of its shape, and this is what's so remarkable about it, no matter where the parallel line hits, so here it's really close to the edge, and here it's closer to the center, and here you can see some at the edge and some closer and some almost at the center. Wherever they hit the parabola, they always reflect in such a way that the line, the ray, goes through the focus. And so if you have a radio wave coming in, and there's lots of very, very, very weak radio waves coming in, then they all bounce off the parabola and they all hit this focus, which happens to be where the receiver is placed. And so a lot of very, very weak radio waves from something that's thousands of miles above us reflects and creates a very strong radio wave focused. That's where we get this word focus, focused in one location. And similarly, the sun's rays are kind of hot. You can go out on a sunny day and get a sunburn because they're hot, but they're not hot enough to actually burn you. The sun's rays wouldn't start a fire unless they're concentrated. And here are the sun's rays, and they're bouncing, and all of them hit this focus, which is where this pot of rice is placed. And so this is great. This is used in a lot of well, not to be insulting, but third world countries, this is a very popular, and first world countries too. Some years ago, I got interested in this technology and I made one of these out of some cardboard and some aluminum foil, and it wasn't very fancy. It wasn't very costly. It was good enough to heat up a pot of rice really on a cloudy day even. Yeah, it really, really works. Here's the other direction. The other direction is this focus is not a receiver, it's an emitter. So you put a light bulb here and light comes out of this light bulb in all different directions because it's a round light bulb. And if the rays from the light don't hit the parabola, then it scatters a little bit. And they're not super strong, but any rays that hit the parabola are sent out from the parabola in a parallel way, and so you get this flashlight beam that all goes in one direction. And so these are kind of neat applications. There are various problems, and I think we kind of know how to do most of them. I mean, this one is easy because there's an x and you can see that it's squared, and there's a y and you can see that it's not. And I gave you last time a tip that when you're dealing with these various conic sections, five of which we will study in this chapter. There's only one conic section that has one variable is squared, here it's the x, and one variable that's not, here it's the y. And what does this make? This makes a vertical parabola like this. And if you see the y is the variable that's squared and the x is the variable that's not, then it makes some sort of horizontal. And which way does it turn? It depends on the coefficient. This one happens to have a -20, and so this isn't a bad picture of this. This one has a -6 in number 23, and so none of these really fit because we know it would have to be upside down. But you can tell from the x that is squared and the y that is not which direction it goes. Similarly, y squared, y that is squared, and x that is not. If you have one like this, x squared plus 2x plus 2y plus 7 equals 0, well, this is a little bit more work. And the reason this is a little bit more work is, well, wait, this one, it's easy to find the center, right? The vertex, rather, of the parabola. It's at -2 It's at positive 1 because I'm taking the negative of this. There's an h and there's a k, if you remember that from last time. This one similarly, make sure you start with the x, don't get fooled. The vertex is at negative 2, this always flips, and positive 3, this always flips, and it goes backwards, right? So it's left and right. So let's go ahead and do this one just because I want to show it to you. Number 25, x squared plus 2x plus 2y plus 7 equals 0. And what we're going to do is, there's an x squared, great, and there's a y, but there's no y squared. And so when we see the x squared and the y not squared, then we know, oh, this is a parabola. We need to complete the square. So here we go. We're going to complete the square. I'll write that. What that means is I need to set it up to complete the square. There's an x squared, 2x, and we know that completing the square will have a plus, and then what? And then what is, I want everything else on the other side. So I'm going to put an equal sign, and I'm going to move my y. I'm going to move my 7, and then there's something that's here. And to be fair, to keep things even, everything has to be the same on both sides. I'm going to add something here to complete the square. I have to add the same thing over here. So x squared plus 2x plus something, and remember how we complete the square. I look at the 2x, and half of 2 is 1, and so I put in 1 squared, and I put in 1 squared, and then here I have the x and I have the 1, so I can say x plus 1 squared equals, and let's figure out what this is. It's negative 2y minus 6, and I want to factor this guy out. So negative 2 times y plus 3. So this is very, very, very nice. Here's standard form. Standard form for a parabola. H is the first letter. H comes before k, and x comes before y. So we know the h goes with the x and the k goes with the y. So standard form, and what have I just found? I've just found that h equals, well, here's a minus h. Minus h is there, and plus 1 is here. And so h must be negative 1. H equals negative 1, and negative 2 equals 4p. And so I can solve that. Well, p is negative 2 divided by 4. So I'm going to say negative 1/2. And then over here, we have a plus 3, which equals negative k. And so k equals negative 3. And we happen to know that the vertex is at hk. If you need to cheat at this, it's not cheating at all. There's a nice formula sheet on page 723, and here the x part is squared and the y is not, and so I know that my shape is something like this, and of course that's not right because my vertex is in the wrong place. My vertex is actually at hk. I just figured out what those are. That's negative 1, negative 3, and I know that the focus should be 0p, but I've shifted by h and k. So 0 plus h and p plus k, and usually they write it as k plus p. And so looking at these values, h is a negative 1, and p is a negative 1/2, and k is a negative 3. And I just plug those in right here for my focus, and I get the point. H is negative 1, k is negative 3, and p is negative 1/2, so that's negative 3 and 1/2. What else do they want to know? Typically, they want to know the directrix. The directrix is a line. It will have a formula like y equals k minus p. And again, looking at k is negative 3, I subtract p. I'm subtracting a negative, so I will add it. And what does that mean? That means y equals negative 3. Oh, let's just write it. Y equals negative 2 and 1/2. That's how you do one of those with completing the square. And you remember completing the square is The main trick is how you set it up. Should we check this one? It wouldn't kill us to check. You open up Desmos and you try it and you see if it looks right. So here comes Desmos, -1, -3, and there's a point. I might as well label it. That's the vertex. And there's also a directrix. So I'm going to put the directrix, y equals -2 1/2. Y equals -2 1/2. And there's this line. And if this is the vertex, here comes the focus. The focus is -1 and -3 1/2. So -1, -3 1/2. And we could label that one too. And so, oh, this one is upside down. I'm thinking, well, that can't be right. But yes, it can, because my p is a negative value. And so this is, we could actually label this. Look at this. This is the vertex. There's the vertex. And this guy is the focus. So I know what the thing should kind of look like. And I can't sketch it, but you can see my cursor moving. It goes like this. And that's where it should be, assuming that I have actually found the vertex and the focus and the directrix. And so now let's key this in, and I'm not going to key in my new fancy version, x plus 1 squared equals, I'm going to key in the original one, because that's how I check things, is always go back to the original problem. So x squared plus 2x plus 2x plus 2y plus 7 equals 0. Yeah, that's where I said it would be. So it seems that I am onto something. This is a fabulous, valuable tool for us to be able to start with an equation and get a shape out of it and know these facts about the shape and how it lies in the plane just by manipulating algebraically these symbols. So this is powerful stuff. I know where to put the, let's go back to it. I'll show you. I know where to put, it's at the top of this page. I know where to put this little receiver, right? And I've created my shape, and of course there are practical considerations. If you're an engineer, then yeah, things matter. You can make some shapes more easily than others in manufacturing. But this is the idea. So there's an example of 10-1, kind of a leftover. Let's do look, if I can find it, let's do look at the sorts of problems you will get. So something like 33 or 34, they give you this drawing, and they tell you there's a dish that's 15 feet wide at the opening. Okay, and the focus is 4 feet from the vertex. And the best way to do this is to draw a little sketch. And if you draw a little sketch, you'll see, well, this is here, and there has to be a line here, and this is 4 feet away, and we know that the focus is 4 feet from the, right, and so you can go the other direction. And then you can figure out how deep this is by looking at the thing that's 15 feet wide. Similarly, with a flashlight mirror, here's the focus. Well, then the directrix has to be on the other side. And here they tell you what the diameter is, and they tell you what the depth is, and you can do these if you needed to. And lots of applications.